So we're going to add our third theorem, actually fourth. Okay, name me some theorems we've done. IVT, the intermediate, what was the requirement of the IVT? Had to be continuous, okay? And so the IVT talks about things that are between, as long as it's continuous, give me any two numbers and I will guarantee you the number between them exists. So that's really helpful when you're given a positive and a negative number, because then you can guarantee a zero will exist, but it can work for anything. It can be two positive numbers, then the number between those two positive numbers will exist. Two negative numbers, the number between those will exist. So that's the IVT, required continuity. Another one? EVT is what we just did. What was the requirement for that?
Continuous and like on the closing.
Continuous and closed. Okay, so continuity is still required for an EVT. We also did the squeeze theorem last chapter. Actually, chapter 2, we did the squeeze theorem. That also required continuity. So today we're doing the mean value theorem. This is the one that has an additional requirement. Not only do you need continuity and do you need a closed interval, but you also need differentiability as well. Okay. All right, so the mean value theorem, the MVT, says if you're continuous and a closed interval and differentiable. So it's three things that have to be true in order for the mean value theorem. So each time we go in our theorems, we're adding a requirement. So the IVT was just continuity. The EVT, continuity and a closed interval. Mean value theorem, continuity, closed interval, and differentiable. So the guarantee is that the instantaneous rate of change and the average rate of change, okay, the word mean can also be substituted for average. So the instantaneous rate of change is the derivative, okay, that's instant. And then the other equation, f of b minus f of a, is the average, also known as mean. That those two things are equal to each other at least once within the closed interval. It could be multiple times that they're equal to each other, but they're equal at least once. Now, both of those things describe slope. The instantaneous rate of change describes the slope along the curve. The average and mean describes the slope of the secant line. So this one is the slope along the curve. And then this side is the slope between the endpoints, which is a secant slope. That's why you have to have endpoints so that you can create the slope. So if the slope along the curve is equal to the slope between the endpoints, what do you have when two slopes are the same? Okay, you did like this. Does it have to be like this, Casey? Can it be like this? Okay, what do you call that? Yeah, when two slopes are equal, you're going to have parallel. So here's a drawing of what that is. So here's a picture. Okay, you have the endpoints from 0, 0 to 2, 4. So you'll have the average rate of change, or the average slope, the mean slope that will connect to the endpoints. But you also have your instantaneous. So we're going to have our tangent slope. And it's going to be running parallel to the secant slope. And you're guaranteed that this will happen once at a minimum. In this case, it happens exactly once. But if you want to find that, then you'll set up the mean value theorem. So first of all, show that the mean value theorem satisfies the hypothesis. So to show that it satisfies the hypotenuse, you would say, all parabolas are continuous. And all parabolas are differentiable. So the MVT applies on the closed interval 0 to 2. Okay, so something like that. So you just have to clearly state it as part of the requirements. Then you can show it. And so since the mean value theorem would apply, then we want to find the instantaneous rate of change, which is 2x, must be equal to f of 2 minus f of 0 over 2 minus 0. So then you just go through the math and you solve that. f of 2 on the parabola is 4. So 4 minus 0 over 2. So 2x equals 2, so x is 1. And so it's going to be happening at 1 along the x-axis. And the graph does support that at 1, the position 1 satisfies the mean value theorem hypothesis that there will be at least one point that's going to run parallel to the secant slope. So you can visualize it and you can work it out algebraically. Okay, here are 4 different functions, but the mean value theorem doesn't necessarily apply to all of them on the closed interval -3 to 3. So the first function, any idea why that would fail? Why would the mean value theorem not apply at x to the 2/3?
Because it isn't going negative, the domain isn't negative, can't be negative.
The domain can't be negative. Give me an example. Like if I pick -1, can I plug -1 into that?
Oh, yeah,
Okay, you take -1, and then what I'd do to that first is I'd square it, which would make it +1, and then I'd take the cube root of it, which is fine. So negatives are okay. Any other ideas? Have you seen that function often enough to know now? Take a look at it. If you don't remember, grab your calculator.
It's non-differential.
Where? Why?
Because if you take the derivative, there's an x in the denominator.
Okay.
It can be, you can't put, so is it 0?
Yeah, Gracie's taking a look at it. What does it look like, Gracie?
Yeah, it's not differentiable at 0.
Why?
It's like a cusp.
Good, okay, it's got a cusp. So there's a cusp at 0. Okay, it looks like this. So it is continuous, and we do have a closed interval, but it's not differentiable there, and so we have a problem. Okay, what about the next one? Can the mean value theorem be applied?
It has a corner.
Corner where?
At 1.
Okay, has a corner. Corner at x is 1, so that makes it non-differentiable. So it is continuous, it does have a closed interval, but it's got a corner, so the mean value theorem will not apply there. All right, how about the next one? Where's the asymptote? Okay, does the mean value theorem apply? Why?
Because it's not continuous.
Where is it not continuous?
At x equals 5.
But what's the interval? Oh.
So it is.
Okay, so the mean value theorem says it has to be continuous and differentiable on a closed interval. This one does have a problem where it's not even continuous, but the problem is outside of the interval. So we would say yes, it is continuous and differentiable, so the MVT applies on the interval -3 to 3. Now, if this had been -3 to 6, then the MVT would not apply because it's not within then the interval would contain the discontinuity. Okay, how about the last one? Asymptote at 2, what does that mean?
It's discontinuous.
So does the MVT apply? Not on that one, okay, because the discontinuity happens within the interval. So that could be like a multiple choice problem. Choose the one that it does apply, or choose the one that it does not apply. Okay. Sometimes they'll ask you MVT in the form of charts with data tables. And they'll tell you, okay, they give us these values are coming from a differentiable function. So we've got a differentiable function, and because it's differentiable, we know it's continuous. What's the fewest number of values of C in the interval 0 to 11 for which the mean value theorem would guarantee that the prime would be equal to 4? Okay, for the prime would be equal to 4. So what are the minimum number of instances that would happen? So the mean value theorem is going to guarantee us. All right, so let's check our different intervals where we would have the prime being equal to 4. So let's check from 0 to 2. What would the interval from 0 to 2 guarantee us that? So we're going to check. What is f of b minus f of a over b minus a equal to when we're doing 2? So f of 2 minus f of 0 over 2 minus 0. So that's going to give us 5 minus 13 over 2. Negative 8 over 2, that's negative 4. Okay, no good. Okay, can you find other intervals where it would be equal to 4? Do some mental math. I'll pause the recording. All right, so if we check 2 to 5, that'll be 17 minus 5 over 5 minus 2. That's 12 over 3, so that's 4. All right, so we've got 1. But it says what's the fewest number of values of C in the interval for which the mean value theorem guarantees? Okay, so it's 1 for sure. Any of the other ones? About 28 minus 17 over 7 minus 5. What do we get there from 5 to 7? Isn't that 11 over 2? Okay. How about 41 over 28, minus 28 over 11 over 7? 41 minus 28. Okay, so that's going to be, 13 over 4? Okay, that doesn't work. But how about some of the other intervals? Like, it doesn't need to just be from 0 to 2. What about like 0 to 5? Or what about 2 to 7? Or what about 5 to 11? Or about 2 to 11? Are there any other ones? You got to kind of think about all of them. Are there any other intervals for which we can guarantee that the f prime would be equal to 4? So 0 to 5, if you check that. 0 to 5 would be 17 minus 13. That's 4, but it would be over 5 minus 0, so that's not going to work. Check 0 to 7. 28 minus 13, which is 15 over 7, and that doesn't work. You check 2 to 11, 36 over 11, nope. Check 2 to 7, 3 over 5, nope, I don't see any others if I'm doing all the math in my head. Okay, so at least once, yeah. About 5 to 11, all right, what do we get for 5 to 11? What's 41 minus 17? 41 minus 17? $24 over, okay, 24 over 6. All right, good job. So she found another one. Okay, so from 5 to 11, 41 minus 17 over 11 minus 5. So we have 24 over 6, which is equal to 4, and we have another one. So when they are giving you data, then they're going to want you to check all the various combinations of the intervals. Okay, maybe they'll give it to you as a graph. Okay, this function is differentiable, continuous and differentiable on the interval based on the graphs. Where are all the values that satisfy the conclusion from 0 to 12? So the conclusion would be that the tangent, that the secant slope must be equal to the tangent slope, which means the secant line must be parallel to the tangent line. So how many times does it look like to you, what are the values where the secant line would be parallel to the tangent line? Where do you think? Give me the x values. X equals 2. Okay, so this one right here, yep, that definitely appears to be parallel. And 9, okay. X is 9 as well, that is parallel. So it appears that this is satisfied at x equals 2 and 9. And those both have the parallel tangent lines parallel to the secant line that's connecting. So the mean value theorem can be asked several different ways. You can be asked off of a graph, you can be asked off of a table, or you can just be asked off of a regular function. All right, here's one, which last year we called them mashup problems. Here's a function where they're asking about, the question is specifically about h, but the table is about what function? F, okay? So we have a combination here. At what value of x from 0 to 4 does the instantaneous rate of change of h equal the average rate of change of f over the interval 0 to 4? So we want the instantaneous rate of change of h, that's h prime, being equal to the average rate of change over the interval of 4. So f of 4 minus f of 0 over 4 minus 0. So do you understand the words instantaneous being equal to average? So they gave us the instantaneous rate of change of h. They gave us 4x e to the x. And then from the table, we will pull out f of 4, which is 7, minus f of 0, which is negative 1, over 4 minus 0, which implies that 4x e to the x must be equal to 7 plus 1 over 4, which is 2. Why do you think they gave some f prime values in the table? Okay, yeah, to check to see if you know that you're not supposed to use prime for average, that if you're doing average, you're just using the values of the function. All right, and then how are you going to solve 4x e to the x equals 2? Suppose you have your calculator, what would you do? Graph it? Okay. What if you don't have your calculator? Algebra? How do you solve something algebraically? No, I'm going to have to factor. All right, so what am I going to pull out here? Pull out a 2. That'll give me 2x e to the x minus 1 equals 0. So I have to try and solve that. I know algebraically is not going to be very easy. So 2x e to the x equals 1. So x e to the x equals 1/2. And there's really, I mean, we can use a natural log. That gets really ugly. Really ugly, really fast. So this would be a calculator problem at this point. Probably set that equal to 0 too. So they won't have you do that. All right, any questions on MVT? We're going to move on. All right, the other thing that pops up in 4.2, and this kind of goes with, Allie, your question about like a plus to a minus. On 4.2, we're really going to start focusing on what the pluses and the minuses indicate, making first derivative charts, so that when we have, if we have a plus, which means f prime is greater than 0, then we're talking about the language of f increases on that interval. And if we have a minus, where f prime is less than 0, then we're talking about f being decreasing. So we're using that language. We haven't quite yet talked about, or what does it mean when we go from a minus to a plus to a minus, or there's no change. But for right now, we're just going to talk about the pluses and the minuses in the first derivative chart. So you would have something like this. On this cubic function, where is it increasing and decreasing? So you're going to go take your first derivative, so 6x squared minus 12, factor that, taking out a 6, so 6x squared minus 2, which is going to imply that x must be equal to 0. The derivative is equal to 0 when x equals plus or minus rad 2. So these are called critical points, right? Because the critical points come from setting the function equal to 0. We should also, for good measure, also take the derivative and set it equal to 1 over 0, but that doesn't give us any solutions. But other problems, especially if they have denominators, might. So we should always check both. Then create the division of intervals. So from negative infinity up to negative rad 2, and then from negative rad 2 up to positive rad 2, and then for everything greater than positive rad 2. And this will be checking the values of f prime. And so you pick a sample value in the interval, something that's easy for you to work with, and you test what the derivative value will come up with. So I'll pick negative 10, because negative 10 happens to be a good number for me to work with. When I take negative 10 and I test the derivative, so I'll square it, multiply it by 6, and subtract 12, I clearly get a positive number. And then in the intervening interval, the middle, I'll pick 0. And when I test 0, 6 times 0 squared minus 12, I'll get negative. So no matter what value I would have tested in that interval, I would have ended up with a negative value. And then I'll test positive 10, which means positive. So I have f of x increases on the intervals negative infinity to negative 2, and on the interval positive 2 to infinity, because f prime of 0, or f prime of x was greater than 0. Okay, so that's the reason. So you state what's happening and why, and the reason always is dependent on what the prime was doing in that interval. So because the prime was positive, then the original function has behavior that is increasing. And then similarly, we would say f decreases on the open interval, negative rad 2 to positive rad 2, because the derivative was less than 0 on that interval. So you don't have to be fancy, just be to the point, and just make sure you cover all the important information, which is the open interval, the behavior, and then the reason why. That should be very familiar.